thank you and welcome to What Physicists Do. Our speaker today is Dr. Milka Nikolic from University of San Francisco. She has her PhD in applied physics and informational science, right?
Yeah, I was programming.
You were programming that, exactly, from University of Belgrade in Serbia. And then she got her PhD in physics from Old Dominion. Her work, I can't read my writing. So I came to know her work when I was visiting the University of San Francisco in the spring and got to see her laboratory. We were just having a chat and finding out how the work of many of the undergraduate students there are developing her laboratory in plasma sciences. So she studies both ways through spectroscopy to study plasmas, and she does some interesting works in very reactive gases, as I understand. But I'm just so pleased that we got Dr. Milka Nikolic to talk to us about plasmas today. Let's give her a warm welcome.
Yeah, hi, I'm Milka, and I am a plasma spectroscopist, and today I'm just going to go over it, how we characterize plasma and why do we do that. So to start with, why plasma is so important? Because it's everywhere. If you want to be an astronomer, working in astrophysics, everything is plasma in the space, and what you do, you characterize plasma. Stars are plasma. If you want to go in high energy physics, again, there is plasma. Tokamak, plasma, you have to understand it to use it. You don't have to go in high energy, you can go in low energy physics and go to material science, and you want to etch a computer chip to put electric circuits on it, you use plasma for cleaning and etching the chips. And then we go to medical physics, that's a field that's developing, and you want to clean the viruses, you want to clean your skin. Again, you can use plasma to clean your hand, to get rid of the viruses, to again, clean anything organic from the surfaces. So plasma is very, very important. So the question is, what is plasma? I'm going to start very, very simple, and people who took quantum mechanics or any kind of modern physics, forgive me for my representation of an atom. We now know this is not exactly true. They have an electron circling around the nucleus, but yeah, this is the limit of my PowerPoint skills. So, circle it is. Let's say I do have a very simplified representation of a simplest atom existing. I have a hydrogen atom that has one proton and one electron orbiting around it in my amazingly circular orbit around it. And guys, realistically, you can't really find one atom anywhere existing on its own, so I'm going to add a couple more atoms here. Again, not more than 6. That's my PowerPoint skills here. But let's say I have a couple of hydrogen atoms orbiting with their electron in their ground state. These are called neutral atoms. And this starts to look like something we can find in nature. That is, usually, you don't get to see an atom on its own. Usually there are a couple of free electrons called primordial electrons just roaming around in the system. And yes, if I have a system that looks something like this, and it doesn't really have to be atomic hydrogen, that's very, very hard to find, and it doesn't really exist on its own. But let's say I have molecules, different atoms, air we breathe. It's a lot of neutral atoms and molecules, hydrogen molecules, oxygen molecules, CO2, H2O, with a couple of these free electrons roaming around, and I get what we call a gas. Now, gas is not a plasma, it's just atoms and molecules in ground state. But what happens if I start heating the gas? Now you can heat stuff different ways. One of the ways, dump a lot of electromagnetic waves on it. We know that electromagnetic waves are energy carried by oscillating electric and magnetic field. And the light we see is a visible light, that's EM wave. Microwaves, electromagnetic waves. Radio frequency waves, electromagnetic waves. They do carry energy. And imagine I dump some electromagnetic waves on my gas. So what happens when I bring energy to the system of neutral atoms and molecules and electrons? So a couple of things, guys, can happen. Some of the atoms and molecules won't change at all. They're just going to continue existing the way they were before I brought the energy to it. They're just going to keep having their electrons in their ground state and being neutral. But it may happen, guys, that some of the free electrons absorb those electromagnetic waves. They take the energy from them. The moment they took the energy, they're going to use that energy to kinetic energy. They're going to start speeding up. Now, my electrons that absorbed a photon can collide with these atoms. If an electron collides with an atom, there are multiple options for it. It can elastically scatter off of an atom. It can also ionize an atom. What does it mean, ionize an atom? An electron collides with an atom, transfers part of its energy to an atom, and the electrons in an atom have enough energy to break the atomic or molecular bond and leave. And you end up with a positive ion and a free electron. That's called the process of ionization, and it can happen. Now, the similar thing can happen that the atom on its own can absorb a photon, get enough energy, ionize an electron, and becomes positive and negative ion. That's less likely, but it still happens. Now, sometimes when an atom absorbs a photon or collides with an electron, here is my another picture, an electron in an atom doesn't have enough energy to break the atomic bond. Remember, even in hydrogen, you need 13.6 electron volts to actually get out of the hydrogen atom. And you need even more and more for bigger atoms and bigger molecules. So sometimes my electron doesn't have enough energy. My electron tries to leave, doesn't have enough energy, and gets what we call an excited state. This is called the process of excitation. Now, guys, we do know now that the electromagnetic wave is oscillating electric and magnetic field carrying energy, and electrons in an atom are waves oscillating with certain frequencies. So when I say electron gains energy and goes to a higher energy level, it just means electron starts oscillating faster, so it has more energy. And a beautiful picture. Let's say my electron went to another energy level. Now, guys, my electron at a higher energy level, it can't stay there. It's not stable for my electron to go there. So what's going to happen? My electron is going to go down and return the energy it took back to the environment. So it's going to return the photon back. That process is called the excitation. Now, guys, depending on how much energy you can give your electron can get more and more energy and try to leave further and further away, oscillating higher and higher frequencies. So it doesn't have to go to what we call first excited state. My electron, my picture here, can go to a second, third, fourth. They're high energy levels called Rydberg states. They're almost a free state for an electron, but still not. The electron is still bound to an atom. It doesn't matter to which level my electron goes, it has to go back. Now, depending on which level my electron went up, it can go back directly to the ground state, or it can cascade down second to first to ground state and emit 2 photons, 3 photons of different energies. At the end of the day, my excited electron goes up, comes down, and returns the same amount of energy it absorbed. It can be the same photon it absorbed, or 2, 3 photons with energies that are going to add up to the energy absorbed originally from my electron. Now, guys, once I make a system like this, where I have some neutral particles that didn't do anything, they didn't even feel the heat coming, some ionized particles, some excited particles, now I have negative and positive ions, a lot of energy emitted by excited particles. This is what we call plasma, or gas discharge. Now, depending how much energy I'm going to dump into this plasma, I can have high temperature or low temperature plasma. Everybody understands stars are high temperature plasma. High energy physics, we work with high energy plasma. I put so much energy into the system that every single electron has enough energy to rip apart all the electrons or some electrons from my atoms. So I end up with all ions. I have positive ions and again free negative electrons. So I have a system that's all ionized, but overall electrically neutral because there was originally a neutral atom and I took an electron out and I got a positive ion and an electron. And that's actually by definition what we call plasma, a system of ionized gas that's overall electrically neutral. Now, it happens that I don't put that much energy into my system. I can put less energy into my system. So not many particles get a chance to be ionized. Low temperature plasmas usually have less than 1% of ionization inside. Most of your atoms are still neutral, but they do get excited, so electrons go up, come down, and emit light. So when you have a system in which most of the particles are neutral, you have less than 1% of ionization, a lot of your particles get excited and go down. We have low temperature plasmas, and actually, truthfully speaking, that's not the true name of it. That's why we have a gas discharge name for it. So usually, if we say gas discharge, it means the low temperature plasma, the one that doesn't have that many ionized particles. We do use in common language both of them, and you'll see in the literature intermittently used, but officially speaking, plasma is ionized gas, where everything was ionized. Now, the beauty of high energy physics and high temperature plasmas is because I ionized everything, so I have free electrons and positive ions, and I put so much energy in it that all my particles are the same. They have the same energies, they have the same temperatures, and that's what we call a thermal equilibrium. So I can characterize it by one quantity. Now, the problem with low temperature plasmas is that everybody's different. I have neutral atoms in ground state. I have multiple excited atoms in different excited states. I have slow heavy ions. I have fast light electrons. Each particle on its own has its own energy, its own temperature, its own velocity. And if you want to characterize it, you basically have to go particle by particle and explain what is the energy, what is the temperature, what is the velocity of how many you have of each. This is an equilibrium. I ionize an electron and have a positive ion. This has everything different. Now, of course, I work in low temperature. Why would I work in something that has thermal equilibrium? So you do understand if you want to work in material science or biophysics, we need to go to these low temperature plasmas. You don't want to give your hand cleaning with the high energy plasmas. You want to work with low energies, which means these are low energy, much, much harder to explain mathematically specifically because you have multiple different particles and they all behave differently. So guys, this is a simplified example, but it's even more oversimplified. In regular plasmas, you have molecules bonded by the same atoms. You have H and H making H2, O2, but then you have H2O, CO2. So you have molecules. So once you start heating the gas, everything can happen. You can start splitting molecules into atoms. Each atom can be ionized. Each atom can be excited. The most important thing that can happen in molecular plasmas is something called the radicals. So if I have a molecule, let's say O2, and I break it apart, I get two oxygen atoms. Now the problem with oxygen is highly electronegative. It has 6 electrons in its last valence shell, and it doesn't like to be like that. So oxygen is always searching for either another oxygen to combine in covalent bond and make O2, or another element that has 2 extra electrons to take from it, that's called ionic bond. All of those neutral elements, so they're not ion, they're neutral elements, but they're highly reactive because they're not in a very incomplete chemical bonding, are called radicals. We need these radicals if we want to do plasma etching and plasma cleaning. We can use other atoms for different stuff. You can just do scattering of surfaces by just bombarding the surface with different atoms, and it's going to scratch and clean the surface. But that's mechanical etching. If you want to do chemical etching, you need one of these radicals, either to clean the surface or to modify the surface the way you want it. So yeah, if we want to do the plasma etching, as I said, we need a couple of the things. First of all, guys, we need a vacuum chamber. So if I want to have a specific gas that's going to bombard my target and etch it, I need to clean the chamber first so I know what I put inside. So to build a plasma etcher, you need a tube and a vacuum pump to pump all the air out. Better the pump, cleaner the inside. Of course, we are not going to get a pure vacuum, but how low pressure you get, the better your etcher is. And then we can set up a very simple experiment where I have 2 electrodes. I have a vacuum chamber where I pumped out all the gas, and then I can pump in something that's going to produce those highly reactive radicals. One mostly commonly used is CF4. It's a carbon tetrafluoride in plasma etching industry, but you can use any. You can use oxygen. I used chlorine when I was in graduate school. We're going to start using oxygen at USF. We're not going to use fluorine. Fluorine is horrible. It's toxic, and it doesn't smell. That's the worst thing. Chlorine, at least you can smell it when it's out. So guys, let's say I do have a chamber, and I put, you can etch anything, but let's say I put a silicon wafer that I want to etch a certain way. I put it on one of the electrodes. I'm going to call it the etching electrode, and then I'm going to put the gas in. And as we talked about it, when I say gas, that means a lot of neutral molecules, couple of free electrons, just sitting there. You can't etch with gas. Gas is not going to do anything. These are all stable. They're just going to be there. But remember what I said. I can heat it. So I'm going to use the radio frequency electromagnetic waves to dump into the system and start heating my CF4 molecules. There's a moment I start heating my CF4 molecules, I'm going to start breaking these bonds. So CF4, most probable process, I'm going to break it in CF3 ion, a fluorine atom, and now I will have 2 electrons. So my electron collides with an atom, gets 1 electron out, I have a positive ion, free radical, and 2 electrons. If my electron doesn't have enough energy to ionize the electron, it can still break the molecular bond. The molecular bonds are the easiest to break. So I can have CF3 atom, again, a fluorine and 1 electron, because I never ionized it, so my original electron just kept on moving. Now guys, we're back to the idea of free radicals. These fluorine atoms, they don't like to be in atomic form. They have 7 electrons, and they need something to bond into a molecule. So they can either bond with another fluorine atom, or, believe it or not, silicon has 4 free electrons that tries to give away. So what will happen is that my fluorine will chemically bond with silicon and produce the silicon fluoride, tetrafluoride, taking pieces of the silicon surface from it. Now, important thing to know here is I'm using radio frequency power. That's megahertz. That's really, really fast oscillating field. That means that my electrodes are switching the polarity very, very fast because it's an oscillating electric and magnetic field. It also means that my light electrons, they do try to follow the field, but my heavy molecules and ions, they don't. They basically just start piling up closer to the electrode. So I do end up having a lot of atoms and molecules here and electrons going up and down. And my fluorine atoms will start etching the silicon surface. Plus, SCF4 is a gas. So you finish the experiment, you turn on, you have your vacuum pump on the whole time. It's just going to pump out everything out of the system. Now, yes, SCF4 is highly poisonous. It's not flammable, but it is poisonous. You don't want to pump it out to the room. So if you start working with highly reactive gases, you have to have a scrubber or some kind of a system that's going to actually make this react with something and usually make either the solid state molecules that's going to just stay in the scrubber. You don't want to stay with SCF4 in your air. But yes, guys, if you can put the patterns on your silicon chip, so you cover the places that you don't want to get etched with a material that's not going to interact with fluorine, you will have only the surfaces you want etched by fluorine, and you just made a computer chip. And that's it. That's in the most basic way how we use plasma etching in science. Of course, depending on where you're working, this can be very, very high advanced, or it can be educational or lower level lab, depending how much money you have to build this. But the process is the same. You have a very reactive gas, you heat it, produce radicals, make them chemically etch with the surface, and etch the surface. As I said, you don't really need the highly reactive gas, you can really use just the mechanical spattering if you want to, but for high precision etching, like those little nanochips that Intel now is making, it needs to be done with chemical etching. By the way, there is a whole science behind how to actually do the design of the wafer before it goes into etching. Which parts of the surface you want to etch, which parts of the surface you want left alone. Yes?
Dr. Nikolic, I mean, this is great. I must say this is a really complete but simple description of, you know, the industry that affects us so much here in the Bay Area, this computer chip manufacturer. And I just wanted to point out, I hadn't really, I mean, obviously think of etching, but you know, that material is going somewhere. So I think it's just interesting to think about the manufacturing of these things is by its nature going to be working with these gases, as you said. And so they need to have some really you know, closed cycle way of getting the silicon that was part of the wafer in this gas that's an unpleasant gas. I mean, this might be, we design the chips in America now, but so many of the chips are made overseas. But you know, I don't know how much of the industry is thinking about that recapture. And I mean, is this beyond the United States where it's carefully thought of when you have these radicals and you're pulling them out and putting them in a scrubber, which is hopefully making some compound out of them? So
a friend of mine, when we were in grad school, he was a mechanical engineer, but he ended up working in my lab a little bit with etching, so he got a job as an engineer at Intel. I know, so you can't talk much because those etching machines are millions of dollars worth and they run day and night. I don't know if you knew that, but the etching machine never stops. There is an engineer on site day and night every day through the year. New Year, Christmas, Thanksgiving, it doesn't really matter. And these are very clean rooms, so you take everything off, you have those white suits, you're covered totally. And I know they put so much effort in their health. I don't know what they do because you basically are not allowed to know, but I know that because he said that it takes him like half an hour just to get into the room with the etcher in it, and then you get out and then you basically like when you're a doctor, you scrub in and you scrub off when you enter the room when you have the etching machine.
But it clearly was an important part of making this a manufacturing technology, was that recapture. And
yeah, this is really important. So when I was in grad school, we worked with chlorine and we didn't know much. So luckily for us, chlorine is a gas that has a smell, so you can smell it. So me and my colleague, we bought the cylinder. So we were working in argon with 10% chlorine to etch the surfaces. And I don't know how it happened, the advisor wasn't there, so we bought the regular pressure regulator for the cylinder. Chlorine is highly corrosive. It ate through the pressure regulator. It exploded. I never thought I can run that fast, but I can. I'm not kidding. So after that, we dedicated a lot of time, and this was a teaching lab, so I was in grad school. So I can only imagine on what level the companies are putting in effort. And we had the scrubbers, and scrubber 1, scrubber 2, to make sure that we were combining, we worked with, I worked in Jefferson Lab on East Coast in Virginia, so I was part of the Old Dominion University. So they make those superconductive radio frequency cavities. And in order to make them superconductive, you actually have to plasma etch it in liquid helium. I know. So those cavities are made of niobium. So the problem in SRF, when you work with chlorine, is niobium pentoxide. And again, it's highly corrosive and it's poisonous. So I know we were putting the scrubbers with nitrogen, so the niobium and chlorine should interact with nitrogen, and then you get the dust, or the solid state, some kind of a dust thing, and then it basically stays in the scrubber, and then there is a service at the university and Jefferson Lab that just deals with how to dispose those chemicals. So yeah, we usually say plasma etching is a very clean process. In a way, you get everything out of your wherever your wafer is, or if you want to make a superconducting radio frequency cavity, everything gets out, so you get very good cavity, but yeah, you have to deal with the residual stuff afterwards. The only good thing is you usually get a gas, so you can get it out of the system, and then you deal with the gas separately. Okay? Okay, so what do I do? So we actually are trying, so by the way, this is my third year at USF, so we just assembled the experiment, so we're basically building everything. So we're trying to get the same thing. I have a plasma etcher, we're gonna try to etch it and get the properties of plasma. So I don't have the etcher from Intel, it's a couple of millions of dollars, and I can't repeat the work of 10 engineers and 50 technicians in an undergraduate lab at USF, but what we can do, we can characterize the plasma that's made inside the etcher, understand its properties, what is the temperature, what is the density, at which pressures you get the most etching, what is the best way to optimize the process. That can be done in a small lab. The beauty of plasma etching, you can do it in a room smaller than this. And if you dispose properly of the reactive gases, and we're not going to deal with anything aside from oxygen, by the way, at USF, so we're going to work with argon, with oxygen. At USF, it's a very clean experiment, and everybody can operate it, and there is a lot to learn if you're an undergraduate student majoring in physics, or any other actual field. So my job is to characterize the plasma. I am a plasma spectroscopist. I am trying to characterize plasma that I will need for plasma etching. That's a specific purpose, but as I mentioned, I'm teaching astronomy classes now, and I love it because I can talk about my research even in astronomy. Because remember what I said, space, all plasma. So going back to my atom, what do? I look at these atoms, molecules, ions, that have those electrons excited to some higher level. And remember what I said, when I have an electron excited to a higher level, it has to go down. And when this electron goes down, it will emit the photon of energy back to the environment. This is my job. I am a photon catcher. I pick up these photons, and based on their energy, on the properties, I can actually tell you anything you need to know about the plasma that emitted this photon. Now guys, we do know that when electron goes up and comes down and emits the photon back to the environment, how much energy of a photon emitted is directly proportional. It's exactly the same to the transition of between two energy levels of my electron. So if I pick up a photon and I find its energy, I know exactly what was the energy transition of my electron that emitted the photon. Now guys, depending on an atom, energy levels of an atom are like a fingerprint. Every atom has its own certain energy level. So knowing the photon and knowing which gas you're working with, you know exactly where the electron had to be to emit a photon of a certain energy. And going all the way back to modern physics, we know that the energy of a wave, which we know electron is a wave, I can't draw it, is directly proportional to the frequency of oscillation, so inversely proportional to the wavelength. Now, if I'm a wave and I'm oscillating, wavelength is just the distance I traveled to make a full oscillation. If I start from the top to the bottom and back to the top. So guys, if I'm a wave and I carry energy, my energy is proportional to frequency, so higher frequency, more energy. It's inversely proportional to my wavelength, so shorter wavelength, more energy. So usually, and you'll see on the pictures I usually put, we in atomic and plasma physics, we like to work in wavelengths instead of the energies, but h is a Planck constant, c is the speed of light. These are constants, so the moment you know the wavelength, you know the energy. It's just the common thing in atomic physics that instead of using energy, we really use wavelengths of light. And by the way, it is sometimes useful because we know that green light, this is 532 nanometers of wavelength. Red light is around 700 nanometers and so forth. So my job is to catch this photon. So how do I catch my photon? Well, there are different ways of catching a photon. What I do, I have a spectrometer with a CCD camera attached to it. So guys, a spectrometer, by the way, it's just a box with a little hole, a slit, through which the light that I'm catching goes through. And then inside my spectrometer, there is a diffraction grating. It's really a piece of equipment with a lot of lines or grooves or holes in it, where my light comes in and refracts or reflects through my diffraction grating. Now, there is a very neat property of light called dispersion, that light at different wavelengths refracts at different angles. So even though I'm going to collect, so first of all, you do understand I never have one atom. That would be awesome. But my plasma has between 10 to the 6 and 10 to the 12 particles per centimeter cube. So I have a lot of atoms in there. So I'm collecting a lot of photons. I'm not collecting one. So all of those photons will come with different wavelengths, different energies, because all of my electrons went to different energy levels. So if I want to sift through them and get specific wavelengths, this is a very, very neat way to do it. I know that of all the light that comes in, and if I combine all colors, visible and invisible, I get white light. But every different wavelength will refract at a different angle. It means if I put another slit here, I can position my slit in a way that I know exactly which wavelength to catch. You usually don't move the slit, you just rotate the diffraction grating inside the spectrometer, but it's a very, very easy way of getting specific wavelengths. Of course, guys, I put the visible light here. That's just a tiny part of electromagnetic spectrum. You can collect infrared. You can collect UV. By the way, to collect UV, a lot of money, very expensive equipment. You can collect any type of electromagnetic radiation. The cheapest way is visible and infrared light, so I do work in that range. I work in visible and near infrared light, but it doesn't matter. The principle is the same. You move the diffraction grating, the light of a certain color will come out. So now I picked up the light of a certain wavelength. Now I have to send it to my computer and actually see it. And that works exactly the same way as any photo camera works. The CCD camera, which is a charge-coupled device, by the way, it's really a little piece with a lot of photocells, two-dimensional on it. So when the light kicks in, it can ionize, it can get the electron out of the cell, and then you can have your electron guided inside of the electric field, get a couple of other electrons, and you get a current, and you collect that current. Knowing what kind of current you collected, you can know exactly what wavelength the light sees. So you're going to see something like this. For a certain wavelength, there is going to be a line. This is called the spectral line. This spectral line tells me exactly what is the energy of the photon I collected, which corresponds to the energy transition of my electron that emitted a photon. Now, this height of this spectral line basically tells me how many photons I collected, because I can collect 1, 10, 1,000, millions of photons. More photons I collect, the taller the spectral line is. Now, guys, when you do collect it with a CCD camera and a spectrometer, this is in arbitrary units. You actually have to calibrate your equipment to a certain number if you want to have absolute values to know exactly are there 1,000 photons, 2,000 photons, million photons, 2 million photons. But overall, the height corresponds to how many photons you emitted and how many atoms in higher level you have. And finally, guys, there is one thing on this picture that's a little bit odd, is that if my electron goes from a higher level to a lower level, it has to emit a photon of a certain energy, meaning every single electron in an argon atom should emit a photon of the same energy. But this is not the same energy. You see how wide this line is? Every spectral line has this broadening. This is called spectral line broadening. And it's due to a lot of things. One of the things is called natural broadening. That's just because of the Heisenberg principle of uncertainty. Because you can know either momentum or mass, right? There are other reasons to broaden the line. One is instrumental broadening. The camera I'm using has its own resolution. It has its own uncertainty. The better the camera, smaller the instrumental broadening, more certain you are in why it is broadened. But it comes from your instruments. Electrons are moving. There is a relative motion between the electron and the spectrometer. There is going to be a Doppler effect. There is Doppler broadening. This is going to be widened also because of the relative motion. If there are strong electric fields, these are going to split into multiple energy levels. That's called Stark broadening. If you have huge magnetic field, it's also going to split those energy levels in multiple energy levels. That's called Zeeman effect. And by the way, yeah, most of the stuff we get from our sun and understand the huge magnetic fields on our sun are because we are observing those Zeeman splittings in the light coming from the sun. When you work in low temperatures and low energies, Stark and Zeeman effect are negligible for us because we have so small amount of energy that electric and magnetic field are not that big to contribute. Most of our broadening comes, and natural is tiny in our case, most of our broadening comes from the instrument, depending how good equipment you have, and the Doppler broadening. By the way, in both instrumental and Doppler broadening, part of the instrumental, the Doppler broadening has the Gaussian distribution of the curve, so that's really nice. So if your dominant broadening is Doppler, you can actually fit it with a Gaussian curve, and just by finding the width of the line, you can find the speeds of the particles that had relative motion to your detecting system. From the speeds of the particles, you can find the temperature of the particles. From temperatures, you can find densities, how many particles per unit volume you have. And yes, Doppler broadening is mostly used to get speeds, temperatures, and densities of neutral particles in low temperature plasmas because they are dominant here. But we can use other types of broadening also to get properties of plasma. So yeah, if you have strong electric fields and there is a Stark broadening, you can actually use Stark broadening to find the density of electrons in your plasma. It's a commonly used approach. Now, aside from just the width of the line, we can talk about this height. How many photons is there? Now, that's also very useful. That also can tell you a lot about your plasma. So one issue is when you do have a detecting device and you start collecting these photons, and more photons is going to get higher and higher, there is a limit in your detecting device, your spectrometer, when it's going to saturate the line. So line is not going to go any more higher, but you're still collecting photons. You have a lot of light, so your lights are going to start spreading out. And that happens. You have spectral lines that are not what we call optically thin. So they are now widened out. So these photons you're collecting, they're not going to just go high up. You start spreading them out. So better way to actually talk about how many photons is not to get the intensity of your spectral line, how tall it is, find the area under the curve. So I have a student who just writes numerical codes to find the area under the curve of all of our data, which will tell us how many photons we collected from the atoms. If we know how many photons, we know exactly how many atoms was there because we know that the energy of an atom is hc over lambda, so knowing the wavelength, we can calculate number of atoms. So yes, that's for what we use the spectral line intensity, or the area under the curve. Get the number of atoms inside it. Now guys, all of this I'm talking about, I'm collecting light, this is all averaged. It's a spatially averaged, it's time average. So spatial average, in a way, we'll talk more because I'm collecting the data from the whole length of plasma. I have no idea where are the atoms that are emitting those photons. Time average is to actually get some significant amount of light that I can use. Usually with spectrometers, you need to have 10, 100, 500 milliseconds of exposure time, just like a regular camera, that you pick up the light and get all the light inside to actually have a measurable spectral line. But 100 milliseconds is a lot. A lot of things can happen in plasma in 100 milliseconds, especially if I have radio frequency plasma that's 100 megahertz of oscillations. So if you want to talk about the time resolution, there are ways to actually get a better camera, and we can use laser-induced fluorescence to actually get how much the number of atoms is changing from the moment you created plasma, and every nanosecond, well, I worked in micro, that was the lowest I got to work, is every couple of microseconds how the plasma changed. That was my graduate work. We don't do it now, but we're building a laser at USF, so we may get there if we get a better spectrometer. The one we have currently is not capable of time resolution, but we are building the laser, so hopefully we'll get there. So guys, going back to spatial distribution, that we can do even at USF lab to see where the particles are. So guys, remember I said here is my very, very simplified atom, and remember what I said. My atom gets excited, emits a photon, I collect it, and I get a spectral line. But it also means that if my ideal circular plasma, of course I'm a physicist, everything is circular, there is another atom on a line that emitted a photon on the same line, I'm going to get more. If I have another atom, I'm going to get even stronger spectral line. There is another atom, and I get even stronger spectral line. Remember, every time I collect a photon, I'm going to get more intensity. So realistically speaking, the intensity I'm collecting is an integral effect. I'm adding all of my intensities and finding the total, which is fine. I can still say there are 4 atoms that have electrons in that excited state. Of course, guys, emitting an electron, it's a random process, so emitting a photon, I'm sorry. When the atom emits a photon, it could have emitting a photon this way or that way, and I wouldn't collect that. But there are statistics and probabilities using Einstein's coefficients that are going to actually tell me, out of the number of photons I collected statistically, how many atoms emitted photons on that line. But it still doesn't tell me where they are. They can be uniformly distributed, they can be collected at one edge. I don't know that. What I do know, I know a collective effect. All of them together will give me this. And it gets even worse. I don't have 4 atoms. Remember what I said? Usually I have 10 to the 12 per centimeter cube. I can't really add up photon by photon by photon analytically. What I do, I take an integral. I take an integral, guys, from the beginning till the end of my plasma and add up all the light collected. What I'm claiming is that every single atom on this line that emitted a photon in that direction came to my total energy. But this is useful. That also means that if I move and take data somewhere else, so here I am, I take data here, I can also see how much light I collected. I can start slicing plasma, slice by slice, and see how much light comes to my detector. I get a distribution at this certain angle, how much light came out of plasma at a certain angle. And you see where I'm going? I can also change the angle, so I can start slicing at different angles. So I can slice my plasma at different angles, and again collect light at every single angle. What I'm going to get is a 2-dimensional integral. For each angle, I have multiple slices, and then I change the angle. By the way, that's how CT scan works. God forbid you go for a CT scan, that's what I'm going to do to you. So they basically scan you, and they see what comes through. So they scan you, look what comes through, and then they slice you like this, and then change the angle, and so forth. So basically they go around your body, just like I'm doing with plasma here. And yes, the thing is, the light that comes out at a certain position P and a certain angle theta is a property of how many atoms are on a line at that certain angle in the length of the plasma. This is actually it's studied very well, and it's called radial integral. Now, mathematically speaking, we're awesome, because if there is a radial integral, there has to be an inverse. And luckily for us, it doesn't have to be, but there is an inverse integral. So it means for us that if I can measure what comes out, I can use the inverse integral to tell me what's inside. And people have derived it. I already used it. There is an integral. It's called inverse radial integral. It will actually tell you exactly by the intensities you measure at certain positions and certain angles, you get exactly the spatial distribution inside a slice of plasma. Now, this is ideal and theoretical. Of course, there's so many issues. There are a couple of big issues. First of all, there is a singularity of P equals P naught, if you want to, because you need to solve this numerically. So it's a huge issue. This is only true if you have a Cauchy principal value integral. So if your plasma is a Cauchy value integral, you're good. If it's not, then you're not good. But there are a lot of developed methods to go around it and actually lower this to a simple sum where you can avoid the singularities and issues. And I worked with a lot of them when I was in graduate school, but I'll talk just about some of them today for you guys.
Dr. Nikolic?
Yes.
You were talking about a student taking over one part, I think it was getting the spectra or summing up the area under the curve. Is this something where what's the software you're using, what's the environment you're using, and have you turned
Okay.
students learned on this, or is it because there exists software that
No,
that
that's
does
actually
this?
all me and the students. Yeah, that's a good point. Everything I do, I like teaching, and I chose USF because it's a primarily teaching institution. So everything I do here is built by me and my students. So everything from the moment we started collecting data, it's me and the students. I started writing softwares, but I have students who are helping me with it. I kind of give them guidances. Is to make this very efficient. You do understand to actually do this, that's a lot of data. You have to slice it at every angle and then move it at every angle. And I'll talk where we are now, we're getting better with it. But all the software to do this, I wrote the basic ones in Fortran, and now my students are translating it in Python. We're getting updated. But yes, I have one student that's really, really interested in computational physics. So he doesn't really want to do any experimental work, so everything he does with me is purely numerical. So he does a lot of numerical calculations for me, and I'll talk more where we are exactly at USF and where I was before. But yes, everything, and I'll go step by step with the experiment, and I'll tell you specifically everything we do. It's really built by me and my students. And we don't have much resources at USF, so, and you'll see the picture of the experiment, you'll understand it then. So everything is built by us and our amazing technicians who are doing an amazing job producing wonders out of nothing. But yes, it's all these codes are actually written by me. You can find them now in Python. When I was doing my PhD a couple of years ago, they weren't there, but now they are. So now students are also comparing the Python codes to what I wrote and writing their own Python code. So we are upgrading my Fortran of all the different approaches into Python 1. And yes, even for the area under the curve, that's just numerical integration. But yes, I have a student who does numerical integration. We also have a code to go through all of our data, gets all the data out, finds the peaks, which are the intensities of the line. I also wrote a code because most of my spectral lines are Gaussian distribution because it's a Doppler effect. Sometimes spectral lines, especially if you don't have a very good spectrometer, overlap. So you have two spectral lines that are overlapped, so you don't know which one's which and which one's area is from which. So me and the student, we're building two Gaussian functions, and they're basically iteratively are changing the parameters until we fit them specifically to our spectral lines, then take them out, and then find the area under the curve. So it's a lot of things. All of the stuff I do is really me and the students. And if you can't find Python codes now, when I worked, there was all, my professor, well, he was a Russian theorist, and he only worked in Fortran, and I had to work in Fortran. So all my codes are written originally in Fortran. Now we're switching to Python, and it's actually a good practice for me too, because I learned Python, but it's actually a good practice for students. A lot of students who want to learn coding and computational physics, I have really nice projects for them. But yeah, this is my experiment. So I took a really quick picture last night. It's not the best picture in the world, but I do have a plasma etcher. It is a vacuum chamber. The little hose here that goes to the vacuum pump. I have two electrodes. This thing here, there is a RF antenna here, so it produces radio frequency electromagnetic waves of 13.56 megahertz. And you can change pressures, you can change powers. We started working in pure argon. We finally collected data in pure argon, so we're going to start in the winter break. We're going to start working with argon and oxygen. We're very excited about it. So, and we're still just worked in plasma, checking what's going on. So from the summer, we're going to start putting the samples in it to actually see. We also have the SEM microscope, so we're going to start etching the surfaces, and then you can look at the surface before and after etching, and you can see the change on it. And I think it's also going to be very, very beneficial to students. But that's our experiment. It's really a little vacuum chamber that I can put the gas in, and you can mix gases. We have a couple of options. But yeah, to take the data, we actually built a little Raspberry Pi robot, which is, again, one of my students' idea, and it worked out perfectly for us. So this thing here, beneath there, it's a little Raspberry Pi computer. So we actually wrote a code to drive two-stepper motors that we attached to those translational sorry?
Stages?
Stages, thank you so much. It's the translational stages, so we have a vertical and horizontal one at this point. So you can take data up and down and left and right, and we wrote a code to actually drive it, and it's a sub-millimeter, so you can go less than a millimeter in a distance. And we drive it with the Raspberry Pi. The beautiful thing is that I hacked into my spectrometer, and now I synchronize them. So the students basically are afraid I'm going to replace them totally at some point, because the moment you start taking data, the Raspberry Pi will move the translational stage. After it's moved, it's going to take the picture, save the data, move it again, take a picture, save the data, go up, go left, go down. So at this point, most of my students just have to take care that plasma stable, the pressure didn't change, the power didn't change, and the thing is moving, because I'm powering this with external battery, so there is a point after 2-3 hours that we drain it and everything just dies. But it was a neat summer project, and Neda and Chelsea, my summer students, did a great job. It is made by physicists, you can see by the amazing design. It also, we used a block of wood to actually move it with it, but I'm not going to go there. The only issue we have now, and we're resolving that, is we can only take up and down, left and right, and we can basically go one angle or the other angle. We can use trigonometry to move the angle, but it takes a lot of time, because we are taking it millimeter by millimeter and then centimeter by centimeter up and down. So I found with the technician a semicircular, like a little ramp that we can drive the thing on. So we're in process of actually purchasing the ramp. So once we put it on, then we can do up and down, left and right, but at every certain angle specifically. At this point, we don't have it, so it's only at the two angles. I will finish, I promise. It took too much time. Currently, we are working only in argon, and it's only because argon is so well studied, especially in plasma etching, that we wanted to make sure we know what we're doing. So everything we measure, we can compare to other people's work before we actually go to oxygen and have some new data that we can claim we understand. So just to make a statement, argon is an inert gas, so this is the electron configuration of the argon, and it has all 8 electrons in its valence level. It means it's not going to combine with anything else, it's just going to be atomic. That's the beauty of argon. So it's not going to make molecules. The moment, guys, you have molecules, you have extra physics and extra math you have to deal with. If you can have an atom, that's really, really nice. And plus, argon is the cheapest gas, atomic gas you can find. Xenon is way, way, way more expensive. So this is the ground state argon. Now from the ground state, remember what I said, if I absorb a photon, I can go to the first excited state. But the first excited state of an argon has actually 4 sublevels. And plus, argon is so well studied that there is a whole notation used in argon that only people who are using argon know. And that's called Paschen notation. So instead of saying this is 3s2, 3p6 level of the ground state, and these should be 4s levels, we have a completely new notation saying 1s2, 1s3, 1s5, and it only works in argon. And then from the first excited, we can go to second excited. It has 10 sublevels, and instead of having 4p, 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 it's actually called 2p, 1, 2, 3, 9, 10. Now guys, when we start exciting argon and making argon plasma, most of the transitions happen between these 2p, which is basically 4p, to these 4s levels. And these are, luckily for us, an infrared spectrum, so we can actually collect almost all of these spectral lines. So what we do, when the electron goes down, we collect the spectral line. That's what I do. I wait for an electron to go from the higher 2p to 1s, which is basically 4p to 4s level, and collect the spectral line. When I collect these spectral lines, I can tell you exactly how many atoms were in this level. Now the nice thing about it, this is not the only transition you can have to the lower level. So there are 2 more from 2p3 level. So if I collect all 3 lines, and they can be different, but if I apply the physics and calculate how many photons exactly was there, I should get the same number. So it's a really good way to cross-reference your data. So out of these 3 spectral lines, all 3 should give me the same number when I calculate how many photons I collected and how many atoms were there. And yes, it's really well studied. There are so many, and we were lucky to collect most of these. Some of those were overlapped, so that's why we worked on Gaussian resolution of light. Luckily for us, we only have Gausses. But we were able to collect a lot of this data. And this is my students. They just finished the graph, so I had to put them on. Take it with caution. We didn't really check much, and we're going to redo a lot of experiments. But this is different energy levels at the constant power of, let's say, 30 watts, and then how they change when we increase the pressure. And we got that almost, and it's too small, I'm so sorry. It's 10 to the 19 per meter cube, which is 10 to the 13 per centimeter cube of particles in the excited levels, which is actually what it's expected in the plasma of our initial conditions. We checked different things. We checked what happens if the pressure is constant, what happens to the power, if I increase the power, how the power is changing. What was really nice, we saw, and I really liked it, and we're going to dedicate more time, is we actually checked at constant conditions, constant power and constant pressure, if we move through the center of plasma from the etching electrode up a centimeter, how the number of particles on average is changing. And it was really neat because it turns out that most of the particles are close to the one for the second electrode. So we kind of expected this to happen, but it was nice to see it actually with multiple energy levels. Now, as I said, we're trying to do spatial distribution too, but we're still waiting for the rotational track. There are, though, ways to work with only one or two angles, but it's only true if you have radial symmetry. So if your plasma is the same everywhere in a circle, then you don't really need to slice it. You can only look at one angle. It should be the same at every angle because it's symmetrical. If that happens, if you have that special plasma that's symmetrical, then your two-dimensional integral becomes one-dimensional integral, and that's called Abel inversion. That's Abel integral. And then you can only take data from one angle. You don't need to slice it. You still have to slice it at that one angle, but you don't have to do every single angle. It should be the same because it's radially symmetric. And this is just the inverse integral you can do. Now, there are papers that claim that even if it's not symmetric plasma, you can still do this by basically expanding this in terms of a Fourier series and just take the first 2 or 3 or 4 elements in a series. And then instead of having two-dimensional integrals, you can actually measure at just 2 perpendicular angles and get 3 one-dimensional integrals. So we found the paper and we applied it just to see what's going to happen and would it work on our plasma. It is just a preliminary work. We are really hoping we're going to slice it at every single angle and get more precise data. But we did slice it. I did test it on x plus y function just to see this is the function. This is me going through Abel integral and, well, Radon integral and the inverse in 3 dimensions. So it's not very perfect, but it's still a can result qualitative result. So we did try. This is what we got. It's really unexpected, and we'll discuss it more, but it turns out we have most of the particles on the, so this is, remember that's the electrode and it's circular. So on the circular electrode, it turns out that in the center we have nothing and then everything is on the edges. What bothers me is that this is the close to at the surface of the etching electrode and then goes up. And compared to the data we saw before, this should be way, way more. This is very, very small number. But then again, we didn't test it much, and it's a work in progress. My students are still extracting data from multiple of these. But it seems that the codes are working, and once we test it, I think we're going to have really nice data. We can actually qualitatively and quantitatively say where are the particles and how many of those we have. And finally, I can stop. If necessary.
We're going to go into questions and such. How many more minutes do you think you need?
I can finish. I can just say one more thing is that this is really important. So all of the stuff I saw, remember, that's my argon, this is ground state, this is the first, this is the second excited, and this is what I measured. We pick up the light that goes from this second excited to the first excited. And there are 4 of these, and there are 10 of these, and there are multiples of lines, but these are, and we only can find the population densities, how many atoms we have in this level. You do understand that what we need are these levels. Now, the problem with the first excited levels is that, first of all, they're so close to the ground state, so even the levels that they're allowed to go back to the ground state, they emit light of such a huge energy. They're all in deep UV light. We can't even collect it. And not just that, there are some rules in quantum mechanics that are called selection rules that don't let you, an electron, go wherever you want to. So when you start going down from the higher energy levels, you can't go anywhere you want to. There are rules that specifically tell you where you can go. So one of these rules doesn't let electrons from two of these sublevels to go back to the ground state. So that's a problem. If my electron cannot go down, it's going to stay here, but it can't stay here. So these levels, and I put them in red, these levels are called metastable levels. My electron cannot radiate. It cannot go down and return the photon back to nature because quantum mechanics doesn't allow it. The only way my electron can go down is actually if this atom collides with another atom and transfers energy in a collision, and then electron goes down without emitting a photon, which goes back to my problem. If the electron doesn't emit a photon, I don't have a photon, I don't know how many atoms is there. On the other hand, these metastable levels are the most important levels in argon if you're working in plasma etching, because they are what we call long-lived. So because my electron cannot go down, usually when the electron goes up and starts going down, it takes in 10 to the negative 9, it's a nanosecond to get there and come down. Metastable levels, it can stay to 10 to the negative 4 seconds. That's what we call a very long-lived atom. And it carries a lot of energy because it never returned the photon to the system, so it can carry that energy and give it to something else. So a lot of etching processes are defined by these metastable levels, and we can't measure them spectroscopically. So the only way to do this is to apply some numerics and some mathematical approaches to actually calculate the values of these by measuring the values of that. And yes, I have students, again, so I have students who like coding, I have students who really like hands-on, so some students built the experiment, and there is a part of my research which is a lot of math, it's purely mathematical. We calculate what contributes to this level. We know that, I don't know, when electron goes up to this level, it populates the level. Electron can also go up from these metastable levels and populate this level, but then it can go down like this. So basically, guys, we write something called the balance equation. Oh no, I'm sorry. What's happened with my equation? It's a mathematical equation that actually from the values we measure and the values we calculate, we can actually get the values of these metastable levels. So I have a student who just works mathematics of this to calculate how many metastable levels is there. Okay, I'm going to stop. I went too far. I'm so sorry. I'm too slow.
We're going to have time for questions, but I would like those of you who need to leave now quickly and quietly in the next minute, basically. Then we'll start with some questions here. We've got until 5:15 for questions. Thank you.
Sorry, I didn't get to meet you, and I can't stay for dinner, but
Dr. Kaminsky, we'll talk. All right, let's begin our question section. Yes, James.
So with the plasma etching, that sounds kind of like a method of depositing your gas particles.
Well, yeah, so you're not, so that's another branch of it. So you can also make thin films. That's another thing you can do.
Okay.
Very good. So there are two options. Either take it off or put it on. So yeah, there is a whole branch of science that just deposits thin films to make different surfaces because it will improve the quality of the material or whatever you use it. Etching is taking pieces of atoms from the surface.
Okay.
But yes, you can deposit the surfaces too. Yeah.
Yeah, that's what I heard. Okay, thank
Yeah.
And then are there doubly ionized states or triply ionized?
Yes, you can have. So I work in low temperature, so you don't even get too many ions. I can't, with the spectrometer I have, I can't even pick up the ionic lines on it. But yes, the more energy pool, you can be double, triple ionized. You can strip the whole atom and just make
250 volts or 500 volts, or what kind of voltage potential is on the electrode?
Yeah, so first of all, I also bias the electrodes, so I make sure that the lower electrode is the etching one. So it's a couple hundred volts for me. Yeah, so we have around 200 volts of biasing on it. And you saw I have small powers. We work in 50 volts, 100 volts. If you, it is, but it not in a way that if you want to really strip electrons, you need to put a lot more power and pressure in your gas. Okay, you first.
When you use radon integrals, does this have a relationship to the radon-Nikodym theorem for the integral?
Radon Nikodym?
Yes.
What does it do?
I'm sorry, I remember this, but like, could you possibly get a reference maybe later to the paper you used for the Fourier analysis expansion of the radon
Yes, it
integrals?
does. Actually, you solved this by Fourier expansion. Very good. So actually, you solve it by doing the Fourier transform between the frequency space and the position space. And then in frequency space, it's easier to work. If you took math methods, you know that. And then you actually work in the frequency space. Very good. And then once you solve for it, you go back to position space and you get these integrals. If you want to, I can share my PhD thesis where I derived it step by step on 15 pages.
Sure.
Yeah, it's there. I usually don't talk about it in the talks.
I think you have a taker for that paper. Yes. On top.
We also published a paper on this.
Beginning of your talk, you mentioned the CF4, to remove that silicon, and then I just wonder how powerful is your plasma, the argon plasma? Does it have any?
No, argon is not going to do etching. So what we did first, and it's just for me to adjust and see where my students are, we just did argon plasma to learn about plasma and learn how to use the experiment and develop the codes. And then we're going to add oxygen. And we're not going to work with fluorine. I don't think university would let me work with fluorine. We're going to use oxygen to actually do the chemical etching of the surfaces. And it doesn't have to be silicon wafer. We are purely educational, so we just want to see what happens when we start etching. No, argon is not going to do anything. Argon is just going to spatter it. You're just going to hit it and get the surface off. But if you want chemical, it has to be some kind of radical.
I have a question on the level of tomography that you have already. You were showing the plot that's showing it's near the electrodes. Am I right in reading that plot that you felt like there were a lot on sort of one edge of the disc
and not
then the
much under the
opposite
other.
and less at the
Yeah,
other?
but
and is it in fact the opposite, or could that?
Yeah, so what we saw when we just did the average one, this is what we saw. So I expected the same thing. So this is closer to the lower electrode, and this is closer to the upper electrode. And the way I saw it, it should be more here. It was just really surprising for me when they sent me the data. But as I said, these are unfiltered. We didn't publish. We didn't show this. You're the first one to see the diagrams.
We feel honored.
This is all my students. They're doing an amazing job. But it's really strange, so we'll have to discuss it, what's going on there. Yes?
Does your spectrometer reveal any information about the refractive index of the plasmas that you're working with? Like based on the amount of dispersion that takes place?
You can. We weren't working on it, but yes, you can. The spectrometer actually has inbuilt, already somebody did it for you. So yes, you can actually find all kinds of properties of plasma. We weren't working on it, but yes, you can.
Steve?
And are color coded, like the 2P is at the 514 line and the 480?
Yeah, so 2P, so these are different. So if I go back, so each of these, so I pick up the spectral line and then calculate the position of the upper level. So 3 of these, and we usually average it. So whatever you get on all 3 of them, they're not going to be exactly the same. Whatever people tell you, they're never going to match exactly, but there should be very close. It also, if some line is not matching, you know that something is wrong, so you discard it. So we usually average these 3 and then see what.
So you work on the 3 and the near infrared, not the 514 green?
No, we are, so it comes with a price. We usually, so most of these are infrared light. And
in the lasers, I would notice a lot of difference with the gas pressure in that, as the pressure goes up, you get more of the green line, and the pressure goes down, you get more of the blue line.
yeah, that's true. So
All things other being equal.
that is with the laser.
With a laser, yeah, with an argon ion.
It will change. Yeah, that's right. as I said, when we take the data, kind of at this point, students are really there to monitor. So they're really, really checking what's going on. By the way, yeah, when you start etching, that's going to change the plasma frequency. It's going to change everything the moment you start etching, so everything changes. So all the data before don't mean anything, because the moment the chemical etching starts, everything will change. The plasma changes color. It's really, really beautiful. So it's purple and then it becomes blue. It's really, you can see the moment when you, visibly you can, so plasma, the argon plasma is purple. So even if you add oxygen, it's going to still be like bright purple. And then you start etching and it's going to go towards bluish color. So you can actually see, and everything, the pressure changes, the power changes. Now, my etcher, I kind of wanted a little bit of a black box because I'm in undergrad institution. So when I was in grad school, I actually built my experiment. This one comes built in, but it has a matching device in it. So the moment the plasma frequency changes, it will match the plasma frequency. So we don't, how much power we put in, some of it will always be reflected just because plasma is oscillating and electromagnetic waves cannot get in.
With the RF.
Yeah, with the RF. So if the plasma, so I do have a matching network. So it matches basically the plasma oscillation. So we can put in a lot of power, so we don't reflect too much.
And focus on those.
Yeah. So yeah, when we were in grad school, we didn't have that. So me and my colleague, we were cutting the solenoid to change the inductance. So to match it physically, it doesn't even work. You have to have an electric circuit that does it for you. Yes.
So you can make plasma by energizing a gas system. So you have a certain amount of energy put into the system, and then over time the energy is released in the form of photons from the plasma. Is there a period of time or like a window you have to work with for how long the energized plasma turns back?
Okay, so that's a very good question. So first of all, there are a couple of options for you what you want to do with your plasma. You can constantly dump energy in it and sustain it. And usually that's what we do in physics. We keep on putting the energy in it, and we produce something called a steady state. We have a balance equation of everything, so everything balances out. When I was in my grad school, we had part of so it was a supersonic flow. So we were dumping a lot of energy. Yeah, it was part of a NASA project, how the vehicles are entering the Martian atmosphere. So you produce a shock wave, which is a plasma. So we were simulating that in the lab. But the thing is, we were putting a lot of microwaves into the cavity where it produced plasma. But then because it was a flow, it kept on moving. So in the afterglow of the plasma, we were producing, we called it a plasmoid, a certain shape of light that sustains on its own without a source of energy, which basically was half of my PhD dissertation, understanding what in the world was going on there. Yeah, but
I'm going to say we're going to take more questions, but we'll take them out in the hall. Let's thank Dr. Nikolic one more time.